AI patent drafting, standardized model training claims that pass Section 112. Welcome! Today we'll turn AI inventions into claims that actually hold up under Section 112. In patent practice, enablement and definiteness are the gatekeepers. Your spec must teach others how to make and use the model, and your claims must be clear. Broad, functional AI claims, like a model configured to detect fraud, invite extra scrutiny unless you show how to achieve the result. In prosecution, clarity beats breadth. Replace buzzwords with concrete steps and parameters. Aim for reproducible training steps, not marketing language. If a practitioner can rerun your pipeline and hit your metrics, you're on the right side of Section 112. Start by nailing the task. Name the input domain, output space, and objective, e.g. Inputs, 224 × 224 RGB images. Outputs, 10 class labels. Objective, minimize cross-entropy. Specify dataset provenance and labeling. Who collected it? Licensing. Labeling protocol, inter-annotator agreement. State the performance metric and threshold. Top 1 accuracy is greater than or equal to 92% on CIFAR 10 test set. Avoid vague claims like optimize performance. Instead, tie performance to a defined benchmark and target. Precision here guides claim scope and supports enablement by telling others exactly what the system must learn and how success is measured. Lay out a stable pipeline. List stages. Pre-processing right pointing arrow initialization, right pointing arrow training, right pointing arrow validation. Tie each to concrete operations. Resizing to 224 × 224. Per channel normalization, Xavier initialization, SGD with momentum, K-fold validation. Identify tunable parameters and ranges. Learning rate 1E5 to 1E3. Momentum 0.8-0.95, batch size 32 to 256. Declare stopping criteria and checkpoints. Stop after 10 epochs without validation improvement, or at 120 epochs. Save best checkpoint by validation accuracy. This structure narrows ambiguity, shows teachability, and signals exactly where variation is permitted. Draft with numbers, not vibes. Quantify with ranges and units. Learning rate 1E5 to 1E3. Weight decay 1E6 to 1E4. Sequence length up to 512 tokens. When you say about, anchor it with experimental tolerance. About 0.9 plus or minus 0.02 F1. Prefer closed sets over open menus. Optimizer is one of SGD, Atom W, not any optimizer. Define tokens for acronyms and jargon at first use. LR denotes learning rate. WER denotes word error rate. Clear, bounded language makes claims definite and supports enablement with evidenced operating regions. If your claim states a function, ground it in measurable outputs. Predict churn probability with AUC is greater than or equal to 0.85 on dataset D. Recite algorithmic steps, not aspirations. Compute embeddings, apply cosine similarity, threshold at tau, instead of identify similar items. Disclose representative architectures, e.g., a 12-layer transformer with 8 heads, hidden size 512, or ARESNET50 with specified blocks. Include example configurations that work. Batch size 128, Atom W at 1E4, label smoothing 0.1. This structure converts a result-oriented claim into a reproducible pathway that examiners and courts can evaluate. Be explicit about data. Describe composition and size. N samples, number of classes, class balance, input modalities. State data splits, train/val/test, with ratios or absolute counts, and whether splits are stratified. Lock down preprocessing steps and order. Deduplication, right-pointing arrow tokenization, right-pointing arrow, lowercasing, right-pointing arrow stop word removal. Or, for images, resize, right-pointing arrow center crop, right-pointing arrow normalize. Detail augmentation policies and bounds. Random crop ±8 pixels. Rotation ±10 degrees. Mix up alpha in 0.1, 0.4. Fixing these elements prevents hidden variability and lets others replicate your reported metrics. Show that it actually works. Provide training script pseudocode that sequences loading data, preprocessing, model init, training loop, validation, and checkpointing. Report hyperparameters and hardware, GPU type, memory, number of GPUs, training time, seed values. Show metric curves meeting thresholds. Validation accuracy, stabilizing above 92%, loss plateauing. Note, early stopping point. Offer ablations to justify parameter ranges. Demonstrate how changing learning rate or dropout affects F1 and identify robust intervals. These embodiments anchor enablement with concrete, repeatable evidence, not just intent. Here's a pattern that reads cleanly and prosecutes well. Preamble, a system/method for task T. Body, clearly defined inputs, processing steps, and parameters with ranges tied to your pipeline. Preprocessing, model architecture, optimizer, learning rate, batch size, stopping rule. Metrics, require a threshold on a named benchmark, e.g., achieves F1 is greater than or equal to 0.88 on dataset D under protocol P. Fallback, add narrower dependent claims limiting to specific architectures, optimizer choices, or data regimes. This layering preserves core protection while offering examinable, enabled paths that satisfy Section 112.